Welcome to our discussion of matter and its properties. What is matter? Well, chemistry is the study of matter. We've discussed this, so we need to talk about what matter actually is. Matter is anything that takes up space, which means it has volume, and has mass. So rocks are matter. A tree is matter, as well as the air around it. And water, also matter. Which of the following are examples of matter? So think about this. A skateboard is matter. Rain, a desk, and air are all matter. Thoughts are not matter. Sounds are not matter. And light is also not matter. Those are forms of energy, and so they do not take up space or have mass. What are the states of matter? Well, matter is divided into these three common states based on how the particles act within a contained space. So when this type of matter is put into a space that's confined, how do they react? And based on those three different ways, we define those as states of matter. And you're familiar, I'm sure, with the three states of matter: solid, liquid, and gas. There is a fourth state of matter known as plasma, and that occurs in lightning and stars. It's a very high energy form of matter, but not one that we regularly discuss in chemistry. So let's take a closer look at solids. A solid has a definite shape and a definite volume. So this rock, for example, the shape is not going to change, and the volume, the amount of space it takes up, is also not going to change. The particles in a solid are tightly packed together, and they do not change shape based on the container that they are in. So if we take a closer look here at these particles, they are lined up in sort of a grid pattern, and they're tightly packed together. And if we put this rock into somebody's bedroom, or we put it out into your backyard, it's not going to change shape. It's going to take up the same amount of space, and it's going to be the same shape. So that's how we define a solid. So if it's moved to a new location, it's not going to change shape. Liquids have a definite volume, but they take the shape of their container. Particles are able to move freely past each other. So these particles in a liquid kind of slide past each other, and they are a little bit more spread out than those in the solid. You can see how it's not quite a regular pattern. And as you, of course, know, liquids change shape as you pour them into different containers. So the particles in this juice are able to slide past each other, and if the juice were poured into another container, the particles would move until they arranged into the shape of the new container. But they would still take up the same amount of space because liquids have a definite volume. So regardless of what container this juice is poured into, there's still the same amount of juice. Gases do not have a definite volume or a definite shape. And the particles of a gas are spread far apart. So you can see these are spread a little more further, quite a bit further apart than liquids or solids. And they can change shape. You could squish this balloon and change the shape of it, and you can also change the volume of the balloon. So the particles in the balloon are far apart and move freely. If the size of the container, here the container is the balloon, changes, the particles will fill the new container because they do not have a defined volume. So if we put this same amount of gas into a larger balloon, it's going to change the shape. It's going to fill that balloon because they do not have a defined shape or volume. So how is matter described? Matter can be described by its physical properties. And we can divide those physical properties into extensive and intensive physical properties. So extensive physical properties change based on the amount of the substance that's present. So if there's more of a certain substance, it's going to have a greater mass. So when we change the amount, the mass changes, and that makes it an extensive property. Same thing with length. If you have a longer piece of metal, or compared to a shorter piece of metal, those are going to be different, and therefore length is an extensive property, and same with volume. Intensive physical properties do not change, regardless of whether the amount of the substance changes. And these are things that we use to identify specific substances, because it doesn't matter how much of the substance we have. These properties are always going to remain the same for that substance. So density, malleability, conductivity, solubility, melting point, and boiling point are all examples of intensive physical properties. This cobalt compound is used as a pigment for paints. Do you think its color is an extensive or intensive property? The correct answer is that color is an intensive property because it doesn't change regardless of how much we have here. If we have a small amount of this cobalt compound or a much larger amount, the color is going to remain the same. Matter can also be described by its chemical properties. So we discussed physical properties. Now we're discussing chemical properties. And a chemical property describes the ability of a substance to react with another substance. And here you can see a reaction occurring with bubbles being formed, which is one of the ways that we know that a chemical reaction has occurred. So this is hydrochloric acid, and it's corroding metal. So there's a piece of zinc in here, and as it corrodes the metal, it's producing those bubbles. So in summary, matter is anything that has both mass and volume. It is commonly found in 3 states based on how particles behave. Matter can be described by physical or chemical properties. What is a pure substance? So matter can be classified into 2 different categories. Pure substances, which are substances that have the same composition throughout and do not vary this composition from sample to sample. So similar to intrinsic properties, these are going to be the same all the time from sample to sample. Examples would be gold, distilled water, or diamonds. A pure substance can be an element or a compound. An element is a pure substance that cannot be chemically or physically broken down into simpler substances. And elements, as you might know, can be found on the periodic table. Examples of elements include magnesium, cobalt, and gold. A compound, on the other hand, is a pure substance that is made of 2 or more substances chemically combined. Examples would be water or table salt, Water is made from hydrogen, which is an element, and oxygen. And table salt is made from sodium and chlorine. And so those elements are chemically combined into these compounds. Gold is an element. So each of these gold bars is made of all gold particles, and the symbol for gold is Au. Nickel chloride is a compound because it's a combination of nickel, Ni, and chlorine, Cl. Those two elements are chemically combined to create this compound, which is a pure substance as well. What is a mixture? So our second category of matter here, we've discussed pure substances, and now we'll discuss mixtures. Mixtures contain more than one type of substance, and they can vary in composition and properties from sample to sample. So compounds were made of more than one type of substance, but they were going to be the same no matter what sample of nickel chloride you had. That's always going to have the same composition. Mixtures, on the other hand, vary in their properties and their components from sample to sample. Examples of this would be sand, steel, wood, granite, and air. So there's a different combination of molecules in each sample of air. Obviously, it's going to be fairly similar, but they can vary. Mixtures can be homogeneous, which means that they are uniformly mixed, or they can be heterogeneous, which means they are not uniformly mixed. And then an additional category of mixtures within this group is a solution. And a solution is a special kind of homogeneous mixture in which one substance is dissolved in another. So we've got a couple of examples here. Air is a homogeneous mixture. So as I mentioned, the components of air can change from sample to sample, but it is uniformly mixed, which is why it appears to be uniform to you. And it appears to look the same, let's say. And so we call that a homogeneous mixture. Trail mix is a heterogeneous mixture. It's not uniformly mixed. There's not the same amount of raisins here as there are over here. Okay, it's just a random composition of substances. And a solution is a special kind of homogeneous mixture. So this is a homogeneous mixture here. It looks uniformly mixed, but one substance is dissolved in another. So in this sports drink, let's say it was a powdered sports drink, that powder is dissolved in water, and that makes it a solution. So if we look at this visually, we can classify matter into different groupings, starting with, can it be physically separated? If it cannot be physically separated, then it's going to be a pure substance. And if that pure substance can be chemically separated or chemically decomposed, in other words, it's made of more than one substance. If not, it's an element. If it is, then it's a compound. And then following our side over here, if the matter can be physically separated, then it is a mixture. If the composition of that mixture is uniform, it's called a homogeneous mixture. If it's not uniform, it's a heterogeneous mixture. And then these homogeneous mixtures can be further separated. If one substance is dissolved in another, then it's called a solution. If not, we just call it a homogeneous mixture. Okay, so let's practice. Are the following substances pure or mixtures? So just going back to this first category here, can it be physically separated? If not, it's a pure substance. If yes, it's a mixture. So pause the video for a second and identify whether you think these are pure substances or mixtures. Okay, copper is a pure substance. It's an element. Table salt or sodium chloride is also a pure substance. It's a compound. Iron filings are made of iron, which is an element, and that is also a pure substance. Sand is a mixture. It has different types of rocks, tiny pieces of rock in it. Sulfur is a pure substance. That's also an element. Milk is a mixture. It's a homogeneous mixture, so it looks uniform, but it is a mixture and can vary from sample to sample. Blood is also a mixture. Gunpowder, also a mixture. A Snickers candy bar is also a mixture. And water is a pure substance. As we discussed, it's made of hydrogen and oxygen, so it's a compound. In summary, matter is classified as either a pure substance or a mixture. Pure substances are either elements or compounds. Mixtures contain more than one type of substance. Homogeneous mixtures and solutions are uniform, while heterogeneous mixtures are not. So most of our chemistry course will be spent looking at pure substances, elements, and compounds. An element is a pure substance, as we established, made of one type of atom. And you'll learn a whole lot more about atoms in the next chapter. For now, let's just say that an atom is a building block of an element. And each element only has one type of atom. All of the known elements are arranged on the periodic table according to similarities in their physical and chemical properties. This is a lump of silicon, which is used as a semiconductor for computers, and silicon is an element that can be found on the periodic table. So here's the periodic table. And each element on this periodic table has a symbol and a name. Here's silicon, for example. Its symbol is Si, and the name is written underneath it. Your periodic table may look different than this, but the elements are all going to be in the same location. What's in the block, the information in the block, may be rearranged a little bit depending on the table, but each element is still in the same location. So silicon actually shares properties with other elements within this column here. And we can also determine some of its properties based on the row of elements that it's in. The rows are called periods, and the columns are called groups. So what is a compound? Well, a compound is formed when two or more elements are chemically combined. So we discussed some examples of compounds like water and salt or sodium chloride. And the properties of a compound can be quite different than those of the elements within it. So it's formed from elements, but it does not necessarily share the properties of the elements that are in the compound. So silicon and oxygen, which we know is a gas, can combine chemically to form silicon dioxide, which is quartz. Notice that the physical properties of silicon dioxide are quite different than the properties of either of the elements that compose it. A chemical formula uses element symbols and numbers to show the proportion of each type of atom in the molecule. And separating a compound into its elements usually requires an input of energy through heat or electricity. So this is carbon dioxide, the formula for carbon dioxide. It's a compound made of 1 atom of carbon and 2 atoms of oxygen. The subscript here identifies how many atoms of a certain element are in the compound. Since C has no subscript, it's understood to be a 1. So there's 1 atom of carbon and 2 atoms of oxygen in this carbon dioxide molecule, and this is known as a chemical formula. Why do compounds have specific atomic ratios? So how do we know that carbon dioxide is always going to be CO2? Well, every compound has a specific ratio of elements that does not change. So there's always going to be 1 carbon atom to 2 oxygen atoms in every carbon dioxide molecule. And here's another example. Sucrose, which is table sugar, is a compound made from carbon, oxygen, and hydrogen. Its formula is C12H22O11. But if the ratio of atoms in this compound were different, the compound would not be sucrose. So this ratio needs to stand 12 to 22 to 11 always, or the compound is not going to be sucrose. And then it would have different properties. In summary, elements and compounds are pure substances. Elements are made of 1 type of atom. Compounds are made of 2 or more elements in a definite ratio that can be written as a chemical formula. Energy can be used to separate a compound into its individual elements. So we've discussed physical and chemical properties, but let's now discuss physical and chemical changes. A physical change is one that alters a substance without changing its composition. So some physical changes also involve a phase change. For example, boiling water converts water from a liquid to a gas, which is a phase change. It's going from one state of matter to another. But the composition of the water particles does not change. They are still H2O. So there's H2O in liquid form in the pot, and there's H2O particles in gas form outside the pot as it's boiling. That's a physical change. It is not changing the composition of those water particles. They are still H2O in either form. A chemical change, on the other hand, is one that converts a substance into a new substance with a different composition. We often call this a chemical reaction. And the original substances in a chemical reaction are called reactants, and the resulting substances are called products. So an example here is rust. That's a chemical reaction. It's formed when iron, oxygen, and water combine to form hydrated iron oxide. What are the reactants and products in this reaction? Think for a second, remembering that reactants are the original substances and the resulting substances are products. So iron, oxygen, and water will be the reactants, and hydrated iron oxide is the product. And this is a chemical change because these substances, iron, oxygen, and water, are changing composition into some new substance. When analytical balances were created, chemists began measuring the mass of reactants and the mass of products. So they measured what went into a chemical reaction and they measured what came out of the chemical reaction to determine how the mass of the reactants and the products compared. Even though chemical reactions were occurring, the mass of the reactants and the mass of the products were the same. So these substances were changing composition, but their mass was being unchanged during the reaction. And this became known as the law of conservation of mass, because the mass was being conserved even though a chemical change or chemical reaction was occurring. The law of conservation of mass states that mass is neither created nor destroyed during a chemical reaction. As an example here, the burning of propane and oxygen produces carbon dioxide and water. So this is the chemical equation that we use to visually show a chemical reaction. And this reaction is the propane and oxygen produces carbon dioxide and water. And the number of atoms of each element is actually the same going into the reaction as coming out of the reaction. And that's why the law of conservation of mass makes sense. The mass from the atoms is going to be the same going in as coming out. And atoms are what are giving those compounds their mass. So we'll get into a lot more specifics on chemical equations and atoms and all of that later in the course, but this is just a quick introduction for you. In summary, physical changes do not affect the composition of a substance and sometimes involve a phase change as well. Chemical changes do change the composition of substances, but the overall mass remains the same throughout the reaction.